The algebraic underpinnings of calculus actually go back before even really the discussion of functions. Our modern notation of functions stems from a very different approach mathematically. So let's go back to talking about numbers. A sequence is an ordered list of numbers. So I've got a sequence here, and I'm calling the things in my sequence A. I have A1, A2, A3, AN. So I've got the first term, the second term, the nth term, and this list extends off to infinity. Within the list, I can think of having a term. I can think of the thing that comes after it would increase my index by 1. We'll call this the successor of AN. And the thing that comes before it would decrease my index by 1. That'll be the predecessor. So every term has a successor. Every term except the first one has a predecessor. There is no requirement that I start the list with a 1. My index could start at 0. It could start at 5. It could start wherever I want. But we just use the counting numbers for convenience. We will frequently find it useful to start a sequence with a 0 instead of a 1. Completely dependent on the situation we're looking at. So far, so good. If I can, it's nice to define a sequence formulaically. If I can come up with some formula for AN, then I have the entire sequence mapped out in front of me. For example, I can write the sequence AN equals N. Now, a lot of textbooks will write a sequence as a set of numbers. I don't want to do that because a set technically is not ordered. It says right up there at the top, my definition is the sequence is ordered. So I tend to write a sequence like an ordered pair as an ordered list. That would be the sequence. And in this case, I would write that as the sequence AN, N starts at 1 and goes off to infinity. Hey, look, a lower limit and an upper limit, just like an integral. Here's another way to write a sequence. Instead of defining the term AN with an equation, I can simply write that sort of sequential notation and put the formula for AN inside that set notation. I would like you to write out the first 4 terms in this sequence, just like we have here for this one. Since the formula for an is a fraction, I should get 4 fractions. And then come back here, thank you. And then some dots. What are the first 4 fractions in this list? You don't have to simplify. Leo?
We started here, so it'd be here and 1 half. 2/3, 3/4.
And then I would say, and so on. Now, you could also write that one as 0/1. Again, I said you didn't have to simplify. It's your call. Again, notice the difference. This sequence started at 1. This sequence started at 0. I could start this same sequence at 2 or 3 or wherever. It would be a different sequence, even if the terms in it are the same. Some sequences have complicated expressions. Bleh. -1 to the nth power times the quantity n plus 1 over 3 to the n starts at 1 and goes off to infinity. All right, wait a second. When n is 1, I get -1 to the first power, which is a minus sign. 1 plus 1 is 2, so the top of my fraction is -2, and then I get 3 to the first, which is 3. What's the next term, Leo?
It would be 3/9 or 1/3.
I'm not going to simplify in this case because I want to see that relation. Why is this one positive?
It's not -1 turns into +1.
Perfect. And then the next one will be negative because it'll be -1 to the third. I'll get a 4 on top, 27 on the bottom. The fourth one, -1 to the fourth, will be positive. 4 plus 1 is 5. 3 to the fourth is 81, and so on. Because of that flip-flopping plus to minus, minus to plus, that's an alternating sequence. What if I wanted a sequence to start positive and then go negative? What if I wanted to try and find an expression that would generate this sequence? I need an extra negative, right? An extra negative means I can write -1 to the n plus 1. It is not always easy to find a formula for a given sequence. We need to start looking for patterns within our fraction. So for example, here's a sequence. Can I find an expression for the nth term in terms of n? Such an expression is called a closed form for our sequence. So that's what this expression is, and this expression, and this expression. Those are closed forms. Now, I see that plus minus routine. You need to make a decision that will affect exactly how you write this sequence's closed form, because you have to tell me what value of n starts us off. Is that n equals 1 or 0, or is it something else? Once you make that decision, your closed form can be then written. But I have to know, is this n equals 1 or 0 or 3 or something else? Okay, well, let's write that. I'm going to write that down so I remember that this is n equals 1, and then this will be n equals 2, n equals 3, and so on. But now I know where I'm starting, and that allows me to choose how to write my flip-flopping signs. Please notice, this is positive. If I'd used n equals 0, I'd write minus 1 to the 0, which would be positive. But you used n equals 1, Dom, so I'm going to write minus 1 to the n plus 1 to make that minus 1 squared, which is positive. Because I need a plus there. And then I have a 3. I'm not quite sure how to get the 3. And I got a 5. So let's look at comparing terms as we go. I notice that the top is increasing by 1 at each step. Second. Which means it's most likely not being multiplied, it's being added. I notice, though, that the bottom is jumping by a multiple of 5 at each step, so that's probably multiplicative. That's like a power or something. Like we had here, increasing powers of 3, I see down here, increasing powers of 5. And that first one is 5 to the first. To get from a 1 for the n to a 3, I add 2. I think this might be the first term. And if I'm lucky, that pattern holds for the second term. So let's now look at n equals 2. Minus 1 to the third would give me a minus. 2 plus 2 would give me a 4. And 5 squared does give me a 25. Now, sometimes it takes more than just a couple. It takes 3 or 4 or 5 before you see a pattern. That's fine. But can you give me an n version of this for the nth term? Leo?
I came up with negative 1 to the n plus 1 times n plus 2 divided by 5 to the n.
And that's what I came up with as well. Gesundheit. Some sequences do not have nice closed form expressions. The sequence Pn is defined by the population of the United States on January 1st of the year 2000 plus n, which means the first term, n equals 0, is January 1st, 2000. The next term is January 1st, 2001. I need to know the population of the United States. I have to go back to census records. Do you have a formula that will tell you the 25th number in this sequence? I can approximate it. I roughly know what the population of the United States should be in January of 2000 25. I don't have a formula for that. Can't pull that out of thin air. I can tell you with 100% assurance that I know the first 10 digits of this sequence. After that, I kind of get lost in it. But I know this begins 1 4 1 5 9 2 6 5 3 5 and keeps going, but I have never needed more than 10 digits of pi in my entire life. By the way, there are competitions to see who can recite from memory the most digits of pi. I think the winner went on for about 22 hours. Ridiculous. There are lots and lots and lots of different formulas that will give me this sequence. But I don't know how to generate each individual term separately without knowing all the ones in front of it. A similar idea. We'll start at 0. F0 is 1. F1 is also 1. And for all n bigger than or equal to 2, Fn is the sum of its 2 predecessors. Not 1, but 2. So how does this sequence work? Well, I start with a 1 and a 1. What's the next number? To get the 0, 1, the n equals 2, F2 is F1 plus F0. 1 and 1 is 2. The next number, 1 and 2, is 3. The next number after that, 2 and 3, is 5. The next number after that, 3 and 5, is 8. 5 and 8 is 13. And so on. This particular sequence is about 400 years old. It appears in a book by the gentleman by the name of Leonardo of Pisa, son of Boccaccio. What we get from the flyleaf, the title of the book. The book is called Liber Abaci, the Book of Counting. Abaci, the abacus, and was designed to introduce people to Hindu-Arabic numerals. Because up until that point, everybody was still writing in Roman numerals. Son of Boccaccio. Anybody know any Italian? Son of is abbreviated in Italian FIB, FIB. The last name ascribed to this author is Fibonacci. This is the Fibonacci sequence. Again, it would be really nice if there was a closed form for this. But because there isn't here, this is called a recurrence relation. Or a recursively defined sequence. In the mid-1800s, a man by the name of Binet would come up. Will you stop that? In the middle of the 1800s, a man by the name of Binet would come up with a method for finding a closed form for all sorts of recurrently defined sequences. And that worked really well. Questions? Hit your mode button on your calculator. Function, parametric, polar, sequence. There is a graphing mode for sequences. All right, wait a minute. A graph of a list of numbers? How the hell does that work? If I use the x-axis like it was the n, then I can just plot each number as the y value. And I'll get a picture of a sequence of dots moving from left to right. And when I go to the y equals menu, each sequence has me give it two pieces of information. The top one is a formula for AN. Now our sequences are U, V, and W. So rather than A, B, whatever, I'll use U. How about we do, let's see, N, where'd the N come from? It's the same button as the X and the T and the theta. The N is right on it. N divided by N plus 1. We know what this sequence starts with. Now, when I did the sequence in our notes, where did I start it? What N value was the first value in that sequence? It was 0, which means I should go up here and change that N minimum to be 0. Then it will start at 0 like I want it to. Oh, and I need to give it the starting value. When I put in 0, I get out 0. Notice that when I hit enter on each of those, it gave it a set of braces in that minimum there. Because you can do more than one minimum value, like our recurrence relation. Zoom standard. Hey, look, a bunch of dots. Now, it turns out that in our window settings, just like for parametric and polar, we now have a range of n. This says we're going to start, oh, wait, I wanted it to start at 0. Let me start that at 0, not at 1. Its default is 1 to 10. And then I can go through, and it tells me how it's going to step through, stepping through by ones. I don't need the negative numbers then. And I know that these y values are pretty small. Look, there are my dots. And if I hit the trace button, it will walk me through 1/2, 2/3, 3/4. That's where we stopped with our list. The next one would be 4/5, and then 5/6, and 6/7. And it'll list me all the numbers. As a matter of fact, I can even go to the table, set the table properly first, starting at 0 and going by ones. And there's my list of sequence values. Questions? I would recommend it to you, if you want to do a lot of graphing of sequences, that you grab the manual for the calculator, because graphing these is a little more complicated. It requires you to actually define two sequences. I don't like graphing recurrence sequences on the calculator. I prefer to do those manually, but that just means drawing a bunch of dots and figuring out the numbers. I want to see more of this list. I'm going to change my window so it goes out to 25, and I'm going to change my ends so they go out to 25. I'll just see more. Before I draw that picture, what's going to happen to my fractions?
Like they close and close to the one. Like they start to level off and happen.
If you think about it, n over n plus 1 can't ever be bigger than 1. Top of the fraction is always smaller than the bottom of the fraction, and each fraction is just a little bit bigger than the one before it, because the top got bigger. This is a calculus class. If I am describing what happens as we keep going and things are getting closer, I'm looking at limits. All right, I'd be saying that the limit as n goes off to infinity of my sequence will be a number. Or I could say, you know, an goes to L as n increases. This is what, chapter 2 where we did limits last semester? So that, let's see, that would be what? January and February? It's been a long time, man. Much less if calculus was not just last semester, but was further back. I'm going to be a pain in the ass. There was a precise way to define a limit. An epsilon and a delta. Remember that garbage? All right, wait a minute. What does this mean? It means that for any epsilon, there is some capital N, so that the difference in the y values is less than epsilon whenever little n is bigger than my capital N. If you've gone far enough down the list, you can make the difference between the dots and the y value that you think it's going towards as small as you want. How often am I going to make you find an epsilon or a delta? Never. But this definition looks awfully effing familiar. And if we turn back to the end of chapter 2, this is the same definition we used for a limit as x went to infinity for a horizontal asymptote. Which means I can match those up. I can think about the limits of functions and the limits of sequences in the same breath. If I have a function f of x and it matches up with my sequence, f of n is equal to an for all n, then I can take the limit of the sequence by looking at the limit of the function. And Leo, that's why I can agree with you that the limit of the sequence we were just looking at is actually 1. If an is n over n plus 1, I'm going to look at f of x being x over x plus 1. Those match up whenever x is equal to n, right? I just changed the letter. But then I know that the limit as x goes to infinity of this function that's a rational function. It's got a horizontal asymptote. How do I find the horizontal asymptote? Leo? I absolutely can use L'Hopital's rule, but because it's a rational function, there's a faster way.
Can you just do like the coefficients of the x's, if they're equal, it equals 1?
That's for the powers of the x's. Since the powers are equal, I use the coefficients.
Yeah.
And that means that I get 1 over 1, which is 1. If they were higher on top, then this would go off to infinity. If the power was higher on the bottom, it would crash down to 0. But you're absolutely right, Leo. I use L'Hopital's rule. The problem is with large rational functions, L'Hopital's rule takes a while. But you're absolutely right. And that means that the sequence goes to the same place. Now, this is interesting for two different reasons, both mathematically geeky. If we think about functions were continuous, right? You drew the curve without lifting your pen. No holes, no jumps, no gaps, no asymptotes, no weirdness. That's what made a function continuous and is what allowed us to do limits. Sequences are the opposite of continuous. There are a bunch of separate dots. So why does the same rule apply? Because here, I was able to replace that sequence of dots with a continuous function. In future calculus classes, if you were to pursue them, we talk about this idea of the set of numbers you are working in having some sort of measure. And the measurement for the real line is what we use for continuity. The jumps in the integers have a different measure. And what we're really saying is the limits in this measure work the same as the limits in this measure. That's a way down the line topic. Questions? If my sequence has a limit, then we say that that sequence converges to that limit. And we call the sequence a convergent sequence. if this limit is infinity, or if the limit doesn't exist, then we say we have a divergent sequence. A large number of bad puns were made over the Maze Runner series of books, convergent and divergent. If we know the limit is infinity, we will sometimes say that our sequence diverges to infinity, but that's neither here nor there. The important part is that it diverges. It turns out that a lot of the results that we have already proved involving infinities and limits have parallels in sequences. 1 over n to the rth power. Wait a minute. Top of that fraction is always 1. If the bottom gets bigger and bigger and bigger, what happens to that as we go off to infinity? Again, it gets closer to 0. R. If I want that bottom to keep getting bigger, I need that R to be a non-negative number. And we did that idea when we were doing improper integrals. Remember, we did the integral of 1 over x to a power? We figured out when it worked and when it didn't. As a matter of fact, a lot of our theorems on functions translate directly to sequences. Things like if you're adding functions and taking a limit, you get the same result as if you add the limits. Page 697 here is a giant list about sequences. And the limit of the sum is the sum of the limits. And the limit of the difference is the difference of the... These are the exact same rules we used for limits back in chapter 2. The limit of a quotient is the quotient of the limits, as long as you're not dividing by 0. The limit of a power is the power of the limit, as long as you're doing positive powers. As a matter of fact, even the squeeze theorem. Remember the squeeze theorem? Squeeze theorem even works for sequences. But my favorite result is this one that's in the box labeled 6. I'm going to write that one down because I use that one an awful lot. A lot of times it helps us to throw out the plus or minus routine and just look at the absolute value of the numbers that are involved. Oh, in which case we're looking at something called absolute behavior. But we can compare things using the squeeze theorem and using a function means I can do all sorts of beneficial things by thinking about functions instead of sequences. I want to look at the sequence ln of n over n. It's not intuitively obvious what's going on here at the beginning, but I know that as soon as n is bigger than 0, this is well defined. And I can replace the n's with an x. So let's do that, and let's look at the function ln of x over x. And I can ask the same question. What is the limit as x goes to infinity of ln of x over x? Yes, Leo?
I think it would be infinity since the bottom is bigger than the top, because ln of 1 is 0 and x is 1.
Yes, when x is 1, but what happens when x is 2 or 3 or 4 or 5? Just knowing what the value is at one point or even a couple of points isn't necessarily enough to tell me what happens all the way moving forward. So let's think about this in function terms. You're right, the bottom is going to go to infinity. What's going to happen at the top? It also goes to infinity. Wait a minute. Now I'm back to needing L'Hopital's rule, because that's infinity over infinity. Oh, okay, let's use L'Hopital's rule. What's the derivative of x? Yay! And the derivative of ln of x is 1 over x. 1 over x over 1 is the same as just 1 over x. Wait a minute, that's 1 over x to a power. That goes to 0. So the limit as n goes to infinity, ln of n over n is 0. As soon as I know what happens to the function version, I know what happens to the sequence version. On the other hand, sometimes, Leo, it is to my benefit to look at particular values. Look at this sequence. Minus 1 to the nth. Wait a minute. If I start with 1, then I get minus 1 to the first, which is negative 1. Minus 1 squared is 1. Minus 1 to the third is negative 1. Minus 1 to the... What do we get? It keeps slipping back and forth. Minus 1, plus 1, minus 1, plus 1. It never settles down on anything. It always stays 2 units apart. Depending on the sequence, a term-by-term analysis may be useful. Okay, this one's with me. I need to know what a term means. What's that exclamation point mean? Yes, Leo.
Factorial.
Which means what?
It's like, enough is like 5 times 4 times 3, so it'd be like n times like a number.
I'm multiplying down. So, n factorial is n times n minus 1 times n minus 2 until I get to 3, 2, 1, stop. How does this help me? Jacob? Okay. But even if I don't cancel it out, I can think of n to the nth as n times n times n, exactly the same number of times, because there are n things in this list and there are n things in this list. Yes? Okay. Hey, wait a minute. Instead of canceling, I want to do a different idea. I want to consider all of the different pieces here. Everything except that very last 1 over n. I'm going to put it in a box. Tell me, what do you know about the number inside the box? Ignoring this part. Yeah.
I can see how both of these would be n cubed, because the top would multiply n cubed, would be the bottom would be n cubed.
But only for those first couple. And remember, there are a lot more in there, right? There are a whole lot of n's here because of all of this stuff, too. Jacob, you were telling me that first n and the bottom n should cancel, right? But then look at the next two numbers. Top is smaller than the bottom. The top is smaller than the bottom. The top is smaller than the bottom. Everything inside that box, if I think of that as one big blob, that number, the top is smaller than the bottom. This number is less than 1. Which means n factorial over n to the nth can never be bigger than 1 over n. You know what else it has to be? It has to be bigger than or equal to 0. Holy crap, I don't have to actually figure out this limit directly. I have the ability to do the squeeze theorem. Because the limit as n goes to infinity of 1 over n is 0, the limit as n goes to infinity of 0 is 0. Therefore, the limit as n goes to infinity of n factorial over n to the n is also 0. Without ever calculating it directly, I was able to stick the squeeze theorem in here. I have more on sequences. So we'll pick this up again on Wednesday, because Monday is the exam. So I'm going to post the key to the review sheet and the key to those 2 homework sessions you just gave me right now. And if you've got questions, you should meet me in office hours this afternoon or email me as soon as possible. I will see you all on Monday. Have a wonderful weekend. Study hard.